Asteroid collision. Two asteroids of equal mass in the asteroid belt between Mars and Jupiter collide with a glancing blow. Asteroid A, which was initially traveling at 40 meters per second, is deflected 30 degrees from its original direction, while asteroid B, which was initially at rest, travels at 45 degrees to the original direction of A, as you can see in the figure. Part A, find the final speed of each asteroid after the collision. Part B, what fraction of the original kinetic energy of asteroid A dissipates during this collision? Okay, so in the system of asteroid A and asteroid B, you can see that there is no external force acting on it. So if I write that the net external force acting on the system is 0, remember that this implies conservation of linear momentum. So the total linear momentum of the system must be a constant. So I can write it two ways. Delta P total is 0, or I can say that the total linear momentum is a constant in this process. So we can write the equation for linear momentum conservation. So we have to note that we have an initial velocity 40 meters per second in I-hat direction for A. For B we have at rest initially, and then finally we have these angles 30 degrees and 45 degrees with respect to the horizontal axis. Okay, so the initial linear momentum of asteroid A was 40.0 m I-hat, so I call the mass of this asteroid m, and final linear momentum of asteroid A will be the magnitude of the final momentum cosine 30 I-hat plus magnitude of the final momentum sine 30 j-hat, because it makes an angle of 30 degrees with respect to the horizontal. So cosine 30 and sine 30 will give me the components. As for asteroid B, the initial linear momentum was 0 because it was at rest. The final linear momentum for asteroid B will be the magnitude of the final linear momentum cosine 45 I-hat minus the final linear momentum magnitude sine 45 j-hat, because as you can see we have a negative component on the y-axis. So if I write the total linear momentum of the system, initially it was 40 m I-hat. And if I write the final linear momentum of the system, it is PA final cosine 30 plus PB final cosine 45 I-hat plus PA final sine 30 minus PB final sine 45 j-hat. So for the x component and y component, this gives me two equations. PA final cosine 30 plus PB final cosine 45 must be equal to the x component of the initial linear momentum, which is 40 m. The y component, PA final sine 30 minus PB final sine 45 must be equal to the y component of initial linear momentum, which was 0. So I note that sine 45 and cosine 45 are the same thing. Sine 45 and cosine 45 are equal to square root 2 over 2. So if I add these two equations, I'm going to obtain PA final sine 30 plus cosine 30 will be equal to 40m. Why? Because sine 45 and cosine 45 are the same thing, so they will cancel when I add them up. So what is PA final? It is mass m times the speed VA final. That is equal to 40m divided by sine 30 plus cosine 30, and here the masses cancel, so this gives me the final speed of asteroid A to be 29.3 meters per second, up to 3 significant figures. Okay, and if I look at the second equation here, this equation, that tells me that PA final sine 30 must be equal to PB final sine 45. Therefore, MVA final sine 30 is equal to MVB final sine 45. The masses cancel, and I find that VB final is equal to VA final times sine 30 divided by sine 45. So this gives me for VB final VA final was 40 divided by sine 30 plus cosine 30, as we have found here. VA final is 40 divided by sine 30 plus cosine 30 multiplied with sine 30 divided by sine 45, and this gives us 20.7 meters per second for the final speed of asteroid B. So let's move on to part B of the problem. Part B of the problem is asking me what fraction of the original kinetic energy of asteroid A dissipates during this collision. Well, what is the original kinetic energy of asteroid A? It is 1/2 its mass m times its speed 40 squared. And what is the final kinetic energy of asteroid A? It is 1/2 m VA final squared, which is 40 divided by sine 30 plus cosine 30 squared. What is the initial kinetic energy of asteroid B? It is 0 because it was at rest. What is the final kinetic energy of asteroid B? It is 1 over 2m because it has the same mass with asteroid A. 40 sine 30 divided by sine 30 plus cosine 30 multiplied with sine 45 parentheses squared 1/2 m VB final squared. So now we can calculate the change in kinetic energy. Delta K is final kinetic energy of asteroid A plus final kinetic energy of asteroid B minus initial kinetic energy of asteroid A minus initial kinetic energy of asteroid B. So this will give us 1/2m VA final squared 40 over sine 30 plus cosine 30 parentheses squared. That is final kinetic energy of A. Final kinetic energy of B, 1/2m 40 sine 30 divided by sine 45 sine 30 plus cosine 30 parentheses squared minus the initial kinetic energy of asteroid A. Initial kinetic energy of asteroid B was 0 because it was at rest. So delta K, the change in kinetic energy divided by the initial kinetic energy of asteroid A is, so we have to divide this by 1/2m 40 squared, that's the initial kinetic energy. We're going to have 1 sine 30 plus cosine 30 squared plus divided by 1/2m 40 squared, we obtain sine 30 divided by sine 45 sine 30 plus cosine 30 parentheses squared, and also divide this by initial kinetic energy, we obtain 1. So if we calculate this, we obtain minus 0.196. So what does that mean? So we see that 19.6% of the original kinetic energy of asteroid A is dissipated during this collision. So we have a loss of 19.6% of the original kinetic energy. Alright, so to summarize, we're talking about an asteroid collision. Asteroid A with an initial speed 40 meters per second traveling in plus I hat direction collides with asteroid B, which was initially at rest. Asteroid A makes an angle 30 degrees with the horizontal axis. B makes a final angle 45 degrees with the horizontal axis. We want to know the final speed of each asteroid and how much kinetic energy was lost. First, we note that the net external force acting on the system is 0, therefore linear momentum must be conserved. So what we need to do is to write the total linear momentum initially and finally. Initially it's 40m I hat plus 0. Finally we have final linear momentum of A, magnitude multiplied with cosine 30 I hat and sine plus sine 30 j hat. For B, we have cosine 45 I hat minus sine 45 j hat. So noting that they have the same equal mass m, we write this equation, and this gives us for x component and y component two equations, and if we add these two equations we obtain VA final, and substituting this value for VA final into this equation we obtain VB final. And then we write the initial kinetic energy of A, final kinetic energy of A, final kinetic energy of B, initial kinetic energy of B. So if we notice that I'm not putting the answers here, rather I'm putting these exact answers into these equations to get a more reliable result. So writing this equation and dividing it by 1 over 2 m40 squared, which is Ka initial, basically this 40 and m's and 1 over 2's disappear, and this becomes minus 1, and this numerically is minus 0.196, so delta K over Ka initial is minus 0.196. If you multiply it by 100, we get the percentage of the original kinetic energy of asteroid A that was lost during the collision.